Hi, I will talk about this paper, Differentially Private Continual Releases of Streaming Frequency Moment Estimations. It's a joint work with Alessandro, Andres, Vahab, Sergei, and Peilin. We're all from Google. Let me start with a motivating example. Chrome has an initiative called Privacy Sandbox, which develops APIs to reduce cross-site tracking while supporting the digital advertising ecosystem. One main component of it is the Flash K-anonymity server, which calls for K-anonymity on several features. For example, to avoid micro-targeting, the server wants to guarantee that a user won't be shown an ad unless some minimum number K of other users are also shown the same ad. The underlying computation problem for the server is just to count the number of distinct elements over a sliding window. Here, we also want the output of the server to be differentially private, since we don't want additional private information leaked to other parties involved in the ad auctions. For example, content publishers, advertisers, and supply-side platforms who work with publishers. Here's the actual model considered in this paper. It's kind of summarized in the title already. We consider the continual release setting in which there are T rounds. In each round, we get input AT, and we need to output the function on inputs received so far. The sliding window setting is a special case of the continual release setting in which the function only depends on inputs from last W rounds. For a particular function, the sliding window setting could be more difficult since you need to handle deletion. The whole talk will mostly focus on the normal continual release setting. And in the end, we will talk about how to convert a continual release setting, continual release algorithm into a sliding window algorithm based on some technique from prior work. The function we want to compute in this paper is a frequency moment. Here we define frequency FA as a number of appearances of A in the stream. And the LP frequency moment is just a sum over non-empty element A, FA to the power of P. For example, L0 frequency moment is just counting the number of distinct elements mentioned in the motivating example. And L1 frequency moment is just counting the number of non-empty elements, or in other words, the sum of binary numbers. For sum, we consider some general setting which numbers don't need to be binary. We also want the algorithm to be streaming, meaning it is a single pass through the stream using small space, sublinear in T. Finally, we want the whole output over T rounds to be differentially private. Informally, it means that if we change one element in the stream, the output distribution should not change by much. And in this paper, all our algorithms are pure DP. Here's our main result. We have a DP algorithm for LP frequency moment estimation. With probability 0.9, it has this approximation guarantee over all T rounds. The first term in the approximation is a multiplicative approximation factor, and the second term is the additive approximation guarantee. The algorithm uses polylog T space. And in this talk, we are counting space in terms of words, which omit the factor caused by the number of bits for recording some function value. In the rest of the talk, I'll talk about the main idea for getting this algorithm. I will start with some special cases of LP frequency moment estimation, and they're also building blocks of our main result. The first algorithm I want to talk about is the binary tree mechanism from prior work, which also initiated the study of differential privacy in a continual release setting. The algorithm is for computing the sum, and it only has additive errors. The error is polylog t, and this is much better than some naive approach, which could have error linear in t. The main idea of the algorithm is to build a binary segment tree, and for each tree node, release the sum of inputs from its segment with some noise for privacy. The guarantee of the algorithm mainly comes from two nice properties of the segment tree. First, any previous sum can be represented by the sum of log t tree nodes. And second, the input of each round is included in at most log t tree nodes. Also, one can show that only all of log t tree nodes need to be maintained during the streaming algorithm. So this algorithm only uses space O of log t. In this work, we also have a new algorithm called grouping for computing the sum. Compared with the previous algorithm, it has better additive error and uses smaller space. The drawback of this algorithm is that first, it requires numbers to be non-negative, and second, it has multiplicative errors. This second drawback might be less of a problem when the algorithm is used as a component for some other problem in which multiplicative errors are unavoidable. The main idea of the algorithm is the following. If the numbers we get in all rounds are large enough, much bigger than the noise, we can simply add noise to each number and output the sum of noisy numbers. This will just give us some multiplicative error. However, in general, we may get some small numbers in some rounds. To deal with these small numbers, the algorithm groups consecutive rounds to make sure that the sum of each group is large enough. Notice that we also need to generate this grouping privately. And for that, we will use an algorithm called above threshold from prior work, which I don't have time to go over. Another thing I want to mention here is that a similar idea has been used in prior work for getting better additive error if the streams are sparse. Next, we consider distinct elements. We start with the easy case when elements are from a small universe. In this case, we can keep a set of appearing elements by using some small space. And we generate a modified stream in which AT is changed to empty if it has appeared before round T. The number of distinct elements in the original stream is just the number of non-empty elements in the modified stream. So we can use the DP algorithm for sum on the modified stream, and we have reduced the distinct elements problem to sum. There's one more subtlety we need to make sure in this reduction is that for two neighboring streams, we want to make sure that their corresponding modified streams don't differ by too much. Actually, we can show they only differ at constant many rounds. Also notice that this idea would work when we have no space constraint, even if the universe is big. Actually, when there are no space constraints, there are more general results which include distinct elements from prior work. For the case with a large universe, we'll try to reduce the problem to the case with a small universe. The main idea here is to use sampling and hashing. We create a modified stream in which each sampled element is changed to its hash value. And now the modified stream has a small universe. And we can use the algorithm from the previous slides to count the number of distinct elements in this modified stream. We try different sampling rates in parallel and find the smallest sampling rate such that the number of these distinct elements of the modified stream is still large enough. We estimate the number of distinct elements of the original stream as the number of distinct elements of the modified stream divided by the sampling rate. This is a good estimation since we can show that there's no collisions between sampled elements with good probability if we use this particular sampling rate. Finally, we are ready to look at the general frequency moment estimation problem. For low frequency elements, we will use a similar strategy as how we count distinct elements. We start by considering the case with a small universe. In this case, we can maintain a set of elements for each low frequency I. We call this set Si. From Si, we can count its size Ci. Notice that at a new round, each Ci is changed by at most 1. And therefore, we can view Ci as a sum of plus minus 1s and 0s. So we can release Ci's privately using the binary tree mechanism. Again, for this to work, we need to make sure that neighboring streams have not very different Ci's. So this gives an algorithm for the small universe. Now for the case with a large universe, we use a similar sampling idea from the previous slides to reduce it to the case with a small universe. For high frequency elements, we use a different technique from heavy hitters. The LP heavy hitters are defined as elements whose frequencies to the power of P are greater than 1 over K times the LP frequency moment of the stream for some parameter K. We first find L2 heavy hitters using consketch. It hashes elements into K buckets and assigns each element a random sign. For each bucket, it computes Zi as a sum of frequencies weighted by the random signs for elements in the bucket. The main idea here is that if a bucket has only one high frequency element together with a bunch of low frequency elements, the absolute value of Zi can be used to estimate the frequency of the high frequency element, as the low frequency element's contribution to Zi canceled out mostly due to the random sign. Again, notice that here Zi is a sum of plus minus 1s, and we can release it privately using the binary tree mechanism. For general LP heavy hitters, we can use a simple reduction from prior work to reduce it to the L2 heavy hitter. To put things together, we use a level set argument from prior work to partition elements into sets of different frequency levels and estimate the set sizes. For small I, corresponding to low frequency elements, we will just use the counts of low frequency elements, which we discussed 2 slides ago. And for large I, it can be shown that there exists some sampling rate such that all sampled elements from II are heavy hitters with good probability. And we can use the heavy hitters techniques from the previous slides of the subsample stream to estimate the size of II. So far, this talk has been focusing on normal continual release algorithms, which computes functions based on all historical inputs. And in these slides, I want to briefly mention that they can be turned into sliding window algorithms using a technique called smooth histogram developed in prior work. The sliding window setting might be more relevant for many practical applications. The smooth histogram technique is basically the following. For smooth functions, they show that a low space continual release algorithm can be turned into a sliding window algorithm with not much worse multiplicative approximation guarantee and space. When we apply this smooth histogram technique to our algorithms, in this work, we also adjust the analysis a little bit to deal with algorithms which have both additive and multiplicative errors. And we also make sure that the DP guarantees don't get much worse. That's all I have. Thanks for listening.